Oh yeah, I got a couple down here. Thank you, Carlos. I met a couple of the younger group coming in too. Yeah, I know there's a couple of people grabbing coffee if you want to wait till those are grabbed and sit down.
Everybody's afraid to sit in the front.
I know, come on.
Cool kids sit in the back.
Yeah.
So no
All the nerds. It's all the nerds that sit in the front.
Or at least the ones that, nerds that forgot their glasses.
Yeah.
So just we're getting set up here. What's everybody's, we already got one response here, but what's everybody's familiarity with barcodes? And, you know, what goes into making them, what goes into making them good, what goes into making them bad, and how you read them easier. So let's say brand new, don't touch them that much, you know, I just scan at the grocery store. What's that level here?
I've been dealing with barcodes and tracking for 30 years.
Nice, okay, good.
From burning our own high salt patches with YAGs, printing with the CIJ 2D matrices in the 90s.
So you've done all the different
I've
levels.
done a lot of application. I'm hoping to learn some more about how it works on the inside.
Yep, and that's really what, you know, kind of the point of this is I expect for anybody that's done some kind of barcoding for some of this to be, you know, pretty rudimentary, but it's meant to be a reminder of all of the levels that go into barcoding so that we don't, you know, as something proliferates out, we tend to forget the basics of how it started. And that's what this should help us with, looking at things like, you know, the sizes of the codes, what part is good, what part is bad. And we'll go through a bit of an exercise at the beginning too of looking at a list of 6 codes, and I'll kind of open it up for everybody to let me know whether they think which of the 6 is going to be the hardest to read or which one is going to be the best. And I think it'll be a good exercise to then go through everything and you know, see what we learn by the end. So my name is Jason Mack. I have been doing barcodes for around 20 years now. Started with just basic sensing, have done very heavily within the medical space. So if anybody has any questions from that side of the world, they are, you know, probably the most stringent when it comes to barcodes, besides maybe military. But you know, everybody has their different uses for barcodes. We'll go over that a little bit too. Anyone have any things they want to make sure we get answered today in the class? Any burning questions in people's minds that want to make sure we get worked in before we go through, but always feel free to ask questions as we go along. All right, so we'll start off kind of just looking at barcodes themselves, make sure we know the nomenclature of what goes into each different type of code, from 1D to stacked to 2D, and then we'll go into a little bit more information about, you know, what they're used for. And then the bulk of what we're going to be going through is, you know, what it takes to read a barcode. And then at the end, kind of talking a little bit more about quality and what it takes to print a good code and how it can go bad and how we might be able to fix that to make, you know, everything along the supply chain easier when using those codes. So obviously, the most basic thing here for anybody that hasn't really used codes, you know, the whole point is a visual representation of a digital piece of information. So, you know, thinking of it, you're really looking at a Morse code type situation. So they are come in lots of different, you know, shapes, sizes, formats, but ultimately you're looking at, you know, digitizing, binarizing information through these visual representations. So why? You know, yes, we have them. What is the point of all of this? Just to make sure we all kind of see where we're using these kind of codes. So originally, the whole point of barcoding and why it came about was to give product ID visibility, meaning, you know, I have a carton of milk, or I have a VIN number on a car, whatever the main thing is we're trying to track. And we just want to know where that, know that that product is what the product is when it comes time for purchasing or transferring of goods. You go to the next stage in the 80s, now you're going to actually look at where that product is from beginning to end. That's the track and trace piece that we typically refer to, knowing where a product was, where it is, and then being able to track where it's going. Obviously, this is very important for just general, supply chain visibility. And then once we have that information, we get into the thing that a lot of people have thought about for the last while, which is the recall piece of it. So now that I have identified, and we'll move into, let's say, a car, for example. We've now identified VIN number with a barcode. This is a serialized car. But I actually want to go beyond that and know line item visibility on that car. So for anybody that has, works with any automotive type barcodes, whether it's just on the weekend, working on a car, I don't know the number they're up to, but it's in the thousands of barcodes in every single car. Because every time something goes wrong, you're going to want to be able to have that information on the exact part, to know the exact line, possibly even the exact worker that worked on installing that in the factory. That way, if there are problems, we can recall all Fords and take it down to recall this very specific set of VIN numbers, because we know that something wasn't running right on this wasn't hot enough, the printers were bad, whatever was happening along that process. So taking that and giving line item visibility. And now if we're doing traceability correct, the next stage, kind of going to the 4.0 method, is actually trying to be proactive about this. So, everything you have here is more reactive. It's gathering the data and then trying to figure out later what we can do with it. Well, now we're finally to that point of process visibility. So how can we take all the data from our barcodes, combine it up with all the other data that we have, and make real-time decisions on, productivity, quality, all of our process in order to, reduce the need for as much labor, reduce the startup cost on new projects, whatever it might be. This is where that data is going to be very useful. And why the quality of the code now matters is if we put all of this time and effort into being good at our process, to knowing where items are along the supply chain, to know exactly what the products are. If we don't have good codes, or we don't have good methodology for reading the codes, then all of that goes out the window. We need that one item visibility in order for us to be useful along the rest of the supply chain. So, and that comes in two parts. One is being able to easily and reliably read the code. I've seen this all too much in factories where, the handheld reader disconnected, so we just let that batch go through. You are only as good in these chains as your weakest point. So if you have areas where you're not able to read the codes, where codes are printed bad and they're damaged to a point that you can't read them, your entire process now is compromised. So this is kind of the why to the whole situation. So let's look at a few of these codes. Again, with not a lot of information to go off of, let's go around the room, and maybe anybody that wants to raise their hand, pick one of these codes that they think is either going to be easy or hard to read, and why you think it's a bad code. Start with one. Do you think that's, let's pick out, who thinks which one of these is the best code? Which one do you think you have the best chance at reading with any generic barcode reading equipment on the market?
I say 5.
Okay, we got a 5. Let's get some more from the rest of the room.
Let's do 5.
Going 5?
I was thinking the bottom of 2, because I don't like the quiet zone around the 5.
Carla, look at you back there.
Jason,
Maybe leading the question here a little bit. All right. Yes.
The remote audience has a hard time hearing the crowd, so if you could.
Yeah, so absolutely. So we've had a couple different 5s out there. Definitely looking like a nice code, as you can see. It looks fairly, printed nicely. And then we've also heard a 2 being a good code. So let's, knowing that we've picked those, so we'll kind of set those aside first. What about 1? Does anybody think might make that tough, or why that is
It's curved, so it's going to be potentially difficult.
Yep, absolutely. So you can see that's some kind of tubing from Home Depot. I've seen this same kind of thing on makeup a lot. Anytime where you have a bottle, you can notice that these labels are placed perpendicular to the curvature, or parallel to the curvature of the item, and you can even see on this part right here where that barcode's starting to fall off the edge. So absolutely, looks like a great code. When it was printed, it might have been the perfect code ever. The second you put it on that product, now that code itself is tough to manage. We'll come back to 2. Obviously, you see the big damage up there at the top. 3. Let's pick someone else that hasn't done it. What do you think might be tough about 3?
I'm going to say because it's red, that
Okay.
it would be bad for a barcode reader.
And do we know why red might be bad?
Because it shows up as invisible on infrared.
On just red, yeah. So it's a very astute. So 3 being a red code on a white background is the key here. So if you are using a red light, which typical barcode reading is done because that end of the spectrum, works best for absorption on sensors. So the red will reflect red light at 100%, and the white background reflects all light at 100%. So if we are only showing red, then we are going to see 100% reflection of all red light across that code, making it basically invisible. And depending on ages of anybody watching this would be the same kind of effect of 3D from comics in the 80s, where there's a blue line and a red line, and you put on glasses so your eyes see the 2 different lines. Same concept here, that we're basically making that invisible. We'll go down to 4. We can obviously see some damage there, direct part mark. We can go over kind of what that damage is actually meaning in real life here, what's actually causing that damage. We'll come back to 5 again at the end of the class, because those are our 2 competitors right now, and then 6. So there are, to preface this before we look at this, there's absolutely allowable to have rectangular codes. It is part of the standard for data matrix codes. Is there anything about this code that someone might think goes against the standard for rectangular codes? And we can come back to it again later, but just when anyone wants to shoot something out.
Cells aren't square.
That's exactly right. So with this,
Can you reiterate that?
What's that?
Can you read
Yeah,
it?
absolutely, yes, yeah. So we heard the data cells aren't square. So when we look at this code on number 6, yes, it's rectangular. But the way it was made rectangular was, in this case, I know, is the user just stretched it. And I've seen this all too often when codes can be created by a number of different individuals, some that have been through knowledge of what's happening with the codes, and others that, may be marketing or maybe production, and they don't know the difference between code and what the data means versus it just being a picture on a product. So in this case, someone wanted to fit the code in an area, and they said, well, I see that you can have a rectangular code, so why don't I just stretch this square code to be a rectangle? That's not how that works. So we'll come back at the end of the class and we can look over what we think about 5 and 2 to see which one we think is going to be the better code to read in general. So now, let's look at 1D codes and what makes up a 1D code. So you have a bunch of lines. We obviously know that's what's happening. You're making a waveform, but the way it's created is to look at ratios. So every code has some type of language built into it, but the language is based on a lettering system. And that lettering system, in this case, is designed by 1x bars, 2x bars, 3x bars, 4x bars. And all that means is that you start with our 1x. So that's our smallest piece of data that we have. And then we're going to make those wider or thinner, both in the spaces and the lines, in order to decode or encode information. If it's a 1D code, when we're talking about these, the x dimension is going to be that thin bar. So we're just talking about the width of that thin bar. And this is how we measure the size of a code typically. A lot of people think, oh, let me just measure the code on a width. Yes, that information is important, but when we're talking about the main part I care about in the barcode, it's going to be that x dimension, also referred to as mil size of a barcode, which is confusing, but that would be 1/1000th of an inch. So a mil is 1/1000th of an inch, not a millimeter. So when you hear that term, specified out in a barcode, either in a grading report from a barcode or when you're actually creating the barcode, that's going to be the either mil or X dimension here. And then when we look at a 2D code, you can see we're looking at it from a square. So it's either direction. It is a square, so we can measure our X dimension in a X or Y, but it's going to be that same width of that piece of information. Again, our smallest decodable piece of data. So now how do we actually make up a code? What are all the elements that make up a code? So you have your symbol width. That's going to be the overall width of the code. The data, when you look here, if I pretend this is my barcode reader, moving my dot across, this is how the data is created, is left to right, right to left on a code. It does have a direction, but depending on the type of reader and what you're using, it usually can handle being in either method. The vertical, the symbol height, is just redundant. So if we think back to that picture before of the tube, and what happens when the code is around the tube like we saw, your redundant information is uselessly spread along the length of the top. So you can get the redundant piece very easily, but the part that actually houses the information is curving around the tube. All you would have to do in that application is turn that code 90 degrees, and all of a sudden it's created to do exactly what a 1D code was created to do, which is be able to exist on a surface, and still be readable. So that's what the height's there for, is purely for redundancy. So you can make that as tall as you want, and honestly, you can start to make that pretty thin, and most readers are going to be able to distinguish it. We just need to make sure that we have the ability to get a single line across the code. So if that's doable, then a reader can read the code. And then when we look at the actual information piece, you have those narrow bars that we talked about. We want to make sure that they're about the same size as the most narrow space. Otherwise, we start to get that code down here that we saw that was overprinted. And then you're going to have a quiet zone. And this is going to be one of the most important things on any of these codes, is you have to have some type of quiet zone on either side so that when the piece of automation equipment, the digital image that's ultimately extracted from here, which will be a waveform, has a starting and stopping. So we know when to read it. If you just had, a sentence without periods, without, spacing, without paragraphs, it's going to be much harder to read. Especially if we take it, and we'll look on some pictures later, of an extreme case where we have a very busy part on a busy background and trying to understand where the code actually exists in there. If I'm a computer and I look at that, with AI and things like that our brain is doing, we may see that there's a code right in the middle of that page. But if we're running our cursor along this word, narrow bar width, or symbol height, and then we keep going across this code, that waveform is not going to look any different across symbol height than it does on the code. It's still going from dark to light, going from dark to light, and then it's going to go more from dark to light to dark to light. So we have to have that space so that the encoding can understand the differences. And we'll go over how that actually works a little bit later. So any questions on 1D codes here? So this would be our first, kind of what codes came out as the very basic Morse code type code. Okay, so then the next iteration of what barcoding came out is stacked. So you take a 1D code and stack a bunch of them on top of each other. Now you have a 2D code. Now, it's not going to hold as much data as what we now think of as, the standard matrix type 2D codes. But you can see something like this PDF 417, which we're used to seeing on things like UPS packages, mail, or USPS packages mail. You have our data bar here in the middle. Checks. People have seen that type of a code on the bottom of a check. They can still be read by lasers, because when I go across, I can see all the information. Try the long distance here, but I can shine a laser across each of those rows and see that piece of code. But you then have these start and stop bits that tell you that it's combined into one code. So when I decode this with some kind of algorithm, I'm going to get all of it in one text string. But really, ultimately, it is still just a bunch of stacked linear codes like you see there in the bottom right. And then what makes it up? So it's all the same stuff we saw before. You have a symbol height, you have a symbol width, except now the one piece we're adding here is the row height. So we always need to know from a resolution, either of a laser dot or of a imager-based product, we need to have enough resolution to see that difference. So you can see right there, now we add that row height in the equation. To be honest, you know, when you look and you'll see kind of the data encoding in a second, overall, it was a stopgap in reading. There are some reasons with high speed that this is still useful, but for the most part, the existence of stacked 2D symbologies is a stopgap in the market to be able to get us to where we really wanted to get to, which was the matrix symbols. Who here has seen one of those, and is any of them that's been more common in your existence than the other? Yeah, everybody's seen one of those, maybe scanned one with a phone, seen them on a product, whatever it might be. There are different types. So a lot of people, may refer to everything as a data matrix or refer to everything as a QR code or just call them 2D codes. But they do have different methodologies on how they read and do have application-specific reasons of why you would use one or the other, just like you would have with any of the other types of codes. So you can see there, and we'll talk about kind of what characterizes a little bit more, but the data matrix is the L pattern. The QR code has the 3 targets that you can see, and then you have the Aztec code with the target in the center. History-wise, data matrix typically is going to be US and Europe manufacturing. That's who really standardized on data matrix. This is, at this point now, an Omron-owned patent. It's gone through lots of different combining of people all the way back from being the military originally with ID Matrix, through a company RBSI, through Microscan, and now part of Omron. QR codes were designed for automotive in Japan by Denso, and typically used in either Japanese automotive or, as most people have seen now, in printed marketing. So that is a common reader being able to be scanned by cell phones. It's not that cell phones are better at reading that, it's just that because of all of the marketing, because of, digital business cards, menus, everything else, that has become the standard, and so that's what's been developed around that kind of reading. And then finally, Aztec. This can hold more data, but it's pretty uncommon out there. There's not a lot of applications using Aztec anymore. It has fallen the way of HD DVDs and Betamax and all of the other alternative technologies that didn't gain wide usage. So now that we're looking, we saw how the other codes were combined and what made up those. Now let's look at the matrix type codes. So now it's 2-dimensional data. You have a square-shaped cell, and you'll see that cell existing, all over the code. If it's on the inner part, which we can see everything here, that inner grayed out part on the blackened part at the bottom, that's your data. That's where the data exists within the code. It is redundant data, so unlike the 1D code where the redundancy was in the height, now we encode in both directions. So our redundancy is in the actual algorithm itself, typically called ECC 200 is what the main one used now if you're encoding codes. But all of that data, you can damage that on the inside, and there are other bits that will pick up the slack on the code. But the important part here is we get back to that quiet zone that we had on the other codes. Here we're looking at an L pattern. That's the locate for data matrix, or that's the targets in the QR code. That's what's going to help us find this code and find the size of the code. So that's what, when you look at algorithmically how barcode readers are going to go out there and try to find codes, they're going to look for a square, and then they're going to look for the L pattern to orient the code in one direction. Then it's going to use that clock pattern that you see on off around the top and the right, and that's what's going to define where the data is internally. So once you have that information, it's going to overlay a grid and then decode the data. And that's the basics of how barcode reading algorithms are going to work. And we can get into how you can make that signal, which we have here, a signal, to make the noise less and the signal higher so we can encode data and then read it out more regularly. Everything that you see at the top, as well as what we showed there around the outside as the quiet zone, that's all going to be considered the fixed part of the pattern. And that term will come up other times, but that is fixed, and then the data obviously being our data region of the code. And you can see kind of the point here now. At the top, it shows the same exact information in all those codes, all printed at the same resolution as well. So you can see what a code 39, and actually, reasonable code 128, definitely one of the smaller of the 1D codes, but you can see how much more information we can get to a small area with that data matrix code. So this is where everything is going, including UPC codes in the next 6 years. So for the most part, with the way technology is going, 1D codes are more or less going to be phased out for any application where it can be, looking more for that data matrix style or QR like you saw on the back in order to house more data as we now produce more things and want to contain more information in one smaller space. And the things you start getting when you go to that 2D type matrix is you start getting 360-degree reading, all in the same area. You're not trying to read it with a laser and have to have that position where we have our line going straight across this long section. That's a long ways to be perfectly even across the laser. You have low contrast reading based on how the actual algorithms work, where we're locating and then overlaying a grid as opposed to looking at highs and lows and creating a waveform that way. And then the error correction, like we talked about. So you can see that's a little Allen wrench or something of that sort, might be a bike pump needle, over top that code. So because there's enough information to locate the code, because that's clean, and then there's plenty of clock pulse, we can just cover that up like that and it's still going to read just fine. All right, so that's the basics of what make up a code. Any questions on any of that information? And now we're going to get into what makes up an imaging system in order to detect the codes next. Okay, so that's going to be the basics of how it works. You kind of saw that animation. We're going to find a way to illuminate it. You're going to have a symbol. That light is going to bounce off of the symbol up into some kind of detection device. That's going to head over to a decoding algorithm to take all of that image-based information and extract the data. And then we're going to output that data in some specific format for the application. So if it's a laser, you can kind of see how that works in the end. It's nothing more than a waveform. It's going to run that laser using an oscillating mirror across the barcode. So you have your laser light hit here. That's going to change angles, which is going to adjust where along this it scans. Usually it's a rotating oscillating mirror of different pitches, which is going to give you the either number of lines if they're angled or how many rotations per second and what the size of that beam angle is. And that's going to run across this code just like that, potentially at 2,000 times per second for a 1D code. Very useful for moving applications, but and very, very useful, 15 years ago when we can move a mirror very fast, but we don't have that kind of high processing speed GPUs that we do now, multi-core processing in order to handle images quickly. Because all you're doing here on that sensor is looking back at quantity of light. We're not trying to decode any kind of information out of the image, it's just on-off. And you can see how that signal looks, and then when you pick your highs and lows, it's going to be digitized into an on-off signal. And that on-off signal with a little bit of quiet zone on either side is going to, give you your exact data out of the system. Now when we go to more of a imaging system, it's going to be a little bit more complicated because now we're not looking at a single point of data over time, we're looking at a full image. So you'll see now our illumination is going to be a little bit more broad. We're not just looking at that one bit of light coming back. We're looking at an array. So light's going to come out. You're going to have two different types of lighting that we're going to want to use for our own power. One is going to be the specular light, that's going to be the light that is the, coming off the angle of incident on the object. So that's going to be what we typically think of as like the bright field of light. When I shine a flashlight in the mirror, where I see the bright spot coming off the mirror, that's our specular light. Then you have diffuse light. Diffuse light's the light that once it hits the surface, it's going to scatter. In that application of a mirror, the reason a mirror works the way it does is that there's not a lot of diffuse light off that mirror. It's typically going to hit and continue in the path in the exact same direction. Diffuse light is what you think of, like what we have in this room, where light's going to hit the wall, that wall light's going to kind of soften and bounce back to all of us in a more even sense. And every surface is going to give you some specular light and some diffuse light. And so now we have to think, using different types of lighting that we can look after kind of the presentation, and how we're going to be able to use that to do the most important thing, which is increase signal, decrease noise. And that's really what it all comes down to, just like any other mechanical or electrical system. So what tools do we have with lighting? So this is the first piece of how we read codes. First is going to be a ring light. Has anybody ever used a ring light, even if it's not in a barcode reading application, maybe with home photography? This is going to be your usually lowest cost type of light, meant to give you as close to a representation of the light coming directly from the camera as you could assume. Obviously, it's not directly in front of the camera because the camera is in the way of where those lights are, but this is going to be when you have fixed mount types of readers. And I can pass one of these around here. I know you've never seen one of these before, but you can see the lights, while that's all part of the actual camera, that would be the same configuration as a ring light. It's around the actual optics. So thinking of that, anything that this might cause as a problem. Having that light being, just right there on either side of the actual imaging, the optical axis there.
Could cause, if you've got it going in a pattern and light comes out in a cone, you could cause some noise surrounding whatever's actually in the direct center of it, depending on the angle of the lights internally.
Yep, so if you want to be straight on, and that's it, so if the lighting may cause some kind of artifact to show up on the object. So if we have a very specular surface that's going to, give us that light, like we showed here, well, we're going to have that specular light that's going to come directly back to that camera if we're aiming down at that surface. And so if we have a surface that's very mirrored, we're going to be blinded by that light coming back, and it's going to be coming directly back into the sensor. Then we have dark field. From the basic eye there, that could look like the exact same type of light. Typically though, you can see here, they're wider. Because what we want to do is we want to get that light out on the outside, and we can do a whole other class on just lighting, but on the outside of the W of lighting. Meaning we're looking at dark field, so we're looking at the exact opposite type of light. We're looking at that diffuse light with no direct light. And we want it to really look, as you can see in that picture up there, from the sides. What do we think that might give us by coming at a low angle like that, as opposed to coming from the top down? Carly, you got this one before. Let's go with, what do you got? Anything you might see with a dark field light, even based on that image, that you might not see with a ring light or something top down?
You might not get the contrast that you need.
So you might not get contrast. Do you know what might cause that? Or you might get good contrast, but anything, it's going to be surface roughness is really what you're going to look at. You're going to see more of the shape of an object than you are what's on the object. So what's actually printed or encoded from colors and lights. You're going to see edges significantly more than you're going to see what the actual object itself is. So depending on how you mark something, that could be a huge advantage, or that could be a huge detractor on your capability of reading.
So if you're like engraving metal, then dark field might be,
Yep.
okay.
Absolutely, yeah. Engraving, especially if it's, it comes down to kind of how the engraving works. So, and what the metal surface is as well. So, if you're engraving, you could be polishing a code actually on a, etched surface. And that, from a dark field, is going to be great. You'll actually see from dark field, the light's going to come in from the sides. It's going to reflect away from the polished surface. And it's going to be very, the diffuse light is going to scatter on the rough surface. So that's how with dark field light you can see those rough surfaces very well and not see the smooth surfaces at all. So absolutely. And then you can do the reverse on objects also. Next we have dome light. And you can see here with dome light, we're not shining light directly down. I know it's a little bit lower, but you can see a big dome like this. We're shining light up. That light's hitting a diffuse surface and then coming back down on our object. So in photography, this would be a light box. That's what you would be thinking of. So when you see those perfectly uniform, nice images where light is even around all sides, that's a dome light. So one of the tough things, though, on the dome light is, let's say, you see right here for the dome light, you're almost right, and that's honestly even a bad picture right there. You're basically on top of the part. If you look over here, I'm over top of the part completely. What would happen with a dome light if you lifted it up a little bit higher? What would it turn into?
A ring light?
It would turn into a ring light. Because the second you get out of the dome, the light's coming from a single spot, and now you're going to be looking at diffuse reflect, or you're going to be looking at that specular reflection as opposed to seeing this, even light. And this is the difference. I mean, for anybody do we have any photographers in the group here? Anybody done any personal photography or even a point-and-shoot camera or anything?
Yeah, I guess.
So if you're doing that, the idea of a nice cloudy day but sunny is like the best way that you can have photography, because the clouds are going to diffuse that light much like a dome here, and you're going to get this even no shadow, not going to pick up any like nose lines or creases or anything like that, which, for professional photography is exactly what you're trying to get away from. And you'll have this nice, evenly smooth image. And then finally we have something called dole lights. So this is on-axis lighting. So you can see we're actually using a prism here to give us the benefits of a dome light without having to be a full dome light. In this case, the light's actually fully on axis. So the ring light, which would be kind of the lower cost version of a dole light, we just put those LEDs around about where the optical axis is. They're going to be a little bit bright, they're going to be a little bit intense. Here we get a very, very even backlight, put it across a prism so that we can look down from the camera straight through the same axis that the light's coming. So the light reflects off that surface, the camera looks through it, the light's able to come back up this side directly through the prism. And that's ultimately how that, it's how a prism works in general, but that's how that prism works. And so we can get very, very even illumination on something that has print or a slightly uneven surface. So we don't see those differences, and we only see the actual color difference. What our eyes typically see when we're just looking at the even sight. So talking about the laser marking of a product, which is typically one of the harder things to look at or mark. Using things like dome and dole lights, we can, if we're encoding actual contrast into the code, meaning it's not just a surface difference, but we're actually making, like burning and changing the chemical composition of the top edge, top layer, and depositing some kind of dark or light material on a etched metal surface. Something like the dole or dome light on this bottom side of the illumination is going to take away all those curves and edges and the striations in the metal and leave it so all we see is the actual marked part of the code. But, in the same note, if you were to take a code and not change the actual color of the code and just do what you were talking about before and change what the surface roughness is, almost scratch the code into the surface, Our dome light is done. We won't see anything. And then depending on how it's scratched, the dome light may give you some reflections. I don't have a slide about it, but has anybody ever heard of dot peen codes? Yeah, decent amount. So lots of head nods. What we're doing with the dot peen code is we're taking some kind of tip and just smashing a hole, an indent into the object. The reason this works very well when we're reading is we're basically making, I don't have a whiteboard or anything, but we're making a V in the bottom of the object. So if we think of the differences between a dome and a dull light here, if we have a perfectly V'd surface and we shine light as a dome, what's going to happen to that surface? Because it's coming from all angles.
No difference in contrast.
It's going to disappear. You won't see anything because you're going to have the same amount of light coming in every angle, and so anything that's going to bounce up to the camera is going to have a hard time coming back and being seen. So now if we look at a dull light, it's all coming on a very specific angle. So if we look at how the dull light's going to work, the light's going to come down into that V, and it's going to reflect off at opposite angles. So it's not going to come back up to the sensor. You may get a little bit of a spot at the bottom where it hits, and comes up. But typically it's going to hit and go off, and hit and go off, and then the other surfaces that are flat are going to come straight back up to the sensor. So now you're going to actually use that use that angle to detect. And you want that harsh V in a dot peen in most applications in order to create that type of mark. And then if you think about what happens with a lot of dot peens, the reason they're done is because you're going to put coatings over them. So now we might need to rethink what the right way to do that. If we had a V, and then the coating came in and filled it so it's more like a low pool, now that idea of using the direct reflections to go off in either way is out the window, because now we have a gradual curve. So now we have to look at the other types of lighting, like dark field, in order to handle that curve of the surface and not see that light. So you can see even the same code, depending where you are in the process and how you create the process, is going to change how you want to read that code. So any questions on just the basics of lighting on a code? And we'll go over examples of each of these types after a little bit there. So then we need to think a little bit more about the actual positioning. So that's all of our lighting systems with a camera aiming straight down. That can be good or bad. Again, we're trying to find ways to use geometries and use all of this technology in order to make reading of codes easier. But you can either pitch or skew, tilt, or actually have a curve of the code. So we already talked about what happens when you have the curve of the code going around. What happens if you were to, in this case, we can kind of look what we have. So what happens if you tilt a code? Do you think that's going to have any problematic effects to reading, given the orientation of that imager? What was that? Most of all, that it might actually have benefits. So it's actually, usually with the tilting, that's what you want. That's actually almost required by most readers because of that direct reflection. By tilting it a little bit, especially for any kind of like paper materials, labels, you want to look at the diffuse, you don't want the direct light, and if we tilt it, let's say this is my barcode, and if I tilt it like this, you'll notice, we know perspective in cameras and our eyes and everything else. This is going to appear closer, or this is closer, it's going to appear larger than this is. So if I was to run a line along the back, yes, a lens has a curve in both directions, so it is more of a triangle, but this is going to be fairly even. And this is still going to be fairly even across the code. And again, that's what we care about, is that waveform. So whether the waveform is huge or it's tiny, I don't really care. I just need a nice waveform. So the tilt is good. I guess that's pitch?
Pitch.
Sorry, pitch. I'm sideways here on what the actual tilt. Tilt is this way. Either way, the pitch, is going to be good. Now, if we take it and we go with the skew here, what happens? As that code is further away here, the data, the waveform that we make is going to be smaller here and then get wider in this direction. So when you read it, you're like, oh yeah, you're supposed to put it at a 30-degree angle, but that angle means so much when you're trying to read. And that distortion, while if it's even, you can compensate for it because all of these, it's easy to run it through some kind of transform to say, okay, that part of the code is progressively wider to here, so let's smush this in when we try to read it. All doable within the reader, but why make situations harder than they have to be? That's just how you add time to process, that's just how you add money to equipment. So, that's again one of the, when you're trying to get that, that's what you're trying to get. And then it adds another piece when we look at what happens to lighting. So if we have this tilted here and I have it angled, then the light that's on this side will actually hit here and possibly bounce right back into the imager. Whereas the light here is going to hit and bounce far away. So you're actually changing how the lighting works if you try to, give it that skew. So we can look at how that kind of actually works on the codes, and we'll go over a few of these on an individual basis. But you can see, what happens when you add a diffuser to light. So trying to not have it be as bright in one spot. You can see how that evens out the light a little bit more. We can, rotate the 90 degrees. What do you think happened with that 90-degree rotation there?
The middle grade.
Yep. So you can see on the left image, we're picking up all that grain because we're going against the grain. So that light's hitting the grain and bouncing back up to the imager. A simple rotation of the part. And look at how much that changes. This isn't things that cost money. This isn't things that change manufacturing of the part. It's just what angle you read it at. And so you can see just that simple will go, it's night and day. That contrast on the right is so much better than what you have on the left just by rotating the object by 90 degrees. So you have low contrast on the bottom and you can change the reading angle there. Curved surface, and we can add different type of lighting. We have reading angle at the bottom again. This is going to have to do with how that's actually been encoded and what the surface looks like. Getting out of that direct light and getting into more diffuse light. And then a dome light on that bottom because of the curved surface. So we can look at these kind of on a more individual basis. So matte surface, a matte label. It's going to be pretty easy. A matte label is designed kind of like we talked about with a dome light to reflect light evenly back. That's the difference between glossy. The quickest way to see this for anybody is if anybody's ever been at a restaurant and tried to read that menu that's already been laminated with all of the harsh lighting above you, and you're like, where can I see this and lean in? You do that on a matte label, the light doesn't reflect directly back ever. It's all diffuse light once it hits. But you can see a little bit of a tilt there. It's going to stay the same. It's not going to change that much because of what that surface is designed to do. It's made to be lit poorly and still read. But what changes with that same thing if it's glossy, just like we talked about. You'll have those bright lights right in the center. Maybe it's the reader. Maybe it's the sun, depending on the application. I have had to fly to another country specifically because the light box that was created to keep out the sun was not fully enclosed at a very low angle. And while our eyes don't notice it, something like light coming through a low angle window or a skylight on the other end of a facility can heavily affect a camera if it's looking straight out at that object. And so you can see what happens when light will come in and reflect off of a surface like that. Just a little bit of an angle, our object is still mostly at the same plane as the image, but the light quickly bounces away from the object. And it's not a hard thing to calculate or look at. It's directly reflecting off, so depending on your distance, your angle needs to be less in order to reflect that light away. Same thing here if we look at a brushed aluminum surface. So we have that bright light in the center. Even if it's diffuse, that light, we're not seeing the edges of the barcode reader that we passed around the barcode reader. Lighting is just on the side. Those are harsh. Even if we diffuse it, use a really nice ring light. You know, when we're direct on like that, we're still gonna have potential problems. It decodes. And when you're reading, this is probably the worst case. Because, and I've seen this all too many times, is, it works. We're good. I turn the reader, I set up the line. I guarantee, you know, the next person will come out and try to set it up the same, and it's going to be a problem every day. And that, like, almost working. If we take away anything from today and learning about barcodes, it's let's get away from the, it worked first try, so I don't need to worry about it. Let's make sure we're using all the tools in our arsenal, or having readers that have all those tools built in so that we can do this correctly from the beginning. Now we're talking about that, the dot peen here a little bit. Again, you could probably get it to decode in the upper left there, but that hot spot on the left ruins our quiet zone. And quiet zone isn't always about not printing something there. We were talking about it from a printing standpoint. But on the same case here with reading, if we were to, you know, just generally look at this quiet zone is the brightest thing on the entire image. And our quiet zone on the other side, which should be the exact same contrast level as the quiet zone on the left side of the image, is the darkest piece of our image. So when we're trying to set thresholds and understand where our, you know, the max amplitude and the min amplitude of our signal are, you know, we're going to be having a really hard time there. So this one we're looking at polarizer effect. Does anybody know what a polarizer is? Anybody not know what, let's go the other direction. I think a lot of people have seen either in class or everything else. Does anybody not know what a polarizer is or does?
I do not know what a polarizer is.
Okay, so imagine taking light and then only allowing light coming from a specific angle to come through. So you have your waves coming in different directions, and you're only allowing light coming from one angle to come through. The reason that's important is what surface that light bounced off of, and if it's passed through any other objects, changing its waveform. So this is what's used, you know, with glasses a lot of times, because what we don't want to get is light that is directly reflected off the front of a glass surface into our eyes, because that's the bright light. We're trying to remove that first bit of very bright light. Same thing with, has anybody, fishermen, worn glasses that have polarizers on them? You can actually possibly see through the surface of the water because of that first reflective surface is being wiped out. In this case, that's the hot spots you see there. Now, it's not going to be 100% effective, but depending on the surface and what it is, this is a great way to eliminate some of that tough to see bright light. Where it becomes really interesting is much like we talked about with that glass surface. So if you have plastic packaging, especially shaped plastic packaging, coming off of the object there, you can see, you wouldn't even know there's a code there. But you put a polarizer on there and that code comes through perfectly, because now we're looking at the contrast on the label, not on how much light's bouncing back off of the packaging. Now the tough one, curved surface. So we've thought of all of this now on a flat surface. Now I turn a surface and now I angle a surface to make it work. Where it gets more difficult is trying to illuminate evenly a curved surface. So if we're trying to do that, what are a couple ways we can make reading, and we have all our arsenal, you know, this is our own process, we're not beholden to anyone else. How are we going to make reading on a curved surface easier? So let's start with lighting. It's already on there, we have to read it. I think my slide gives it away. It's highlighted. But what do you think that dome light gives us that the other types of lighting don't? And when you see the Q, and the Q means you're getting the quadrant, so that's the dark field illumination. If you see north, south versus east or west, this is going to be whether it's the lighting coming from the here and here. Sorry, north, south would be here and here. East, west would be on either side of the curve. So you can see it there. East-west lighting on this is the worst. You'll see nothing because your bar of light, the only light you're going to get that comes back to you on a curved metal surface is going to be that directly reflected light. And it's going to be at whatever angle the light is coming back off at a tangent, you know, to your eye. So you never want to do that kind of lighting. Quadrant looks decent, but again, you're giving a real hard time with those side lights, again, really illuminating here. Our 90-degree lighting is only any of that strip down the middle. For a 2D code, I mean, that's just, you don't see any of the code. 1D code, that's fine, right? Would a 1D code have any problem with this type of lighting? And why is that?
Because the lighting will just flatten out evenly and get everything.
No.
Okay.
But good try, I like it. If it's positioned correctly. Let me you got the head nod there. With a 1D code, I only need to see part of it, if it's oriented correctly, because everything in this direction is redundant. So I only need one strip in the center to be able to read. This is taken advantage heavily in the medical industry with tubes. Should be taken advantage for all product marketing that goes on to small tubes and bottles like makeup and spray bottles and things like that. Typically it's not, because they have other things that are important. But that's why tubes have a long label running vertically on it. And why things like data matrix codes can be tough to do with those type of labels, because you're not redundant in this direction. I want to be redundant in this direction. I want all the data to flow this way. So it's very tough here. Now, that's where the dome light comes in. Now we're getting perfect light, even light from all angles. And that's the most important part. It can't be a couple strips of light. It must be even light from all angles. You can, in this case, you see that it's very dark and we're not getting much light. You can build a system where this will work. You need your bar lights, in this case, to be significantly wider than our actual object. So if we have my curved stylus here in the center, let's say it's right next to it. You can see that my lighting is going to come from here right to this surface, and from here to this surface. You are going to get lighting on all parts of the object. Now, the light up here is going to be bright, and I don't know how in the world I'm going to get a camera in between there. You can have an angle and help, but that light is going to get to all surfaces. But the second you move this object away, which typically is what happens in manufacturing, is because I can't have everything touching, now all of a sudden that angle is only going to get that bit of the surface that gives me my same angular reflection off of the product. So you can find ways to get around it, but that's where cost and difficulty comes up, and you really have to think about what's important for the application. And we'll see that with a couple other codes as well, and I'll have this set up afterwards for anybody that's here in person to play around with a dome light and look at what an object looks like versus, what low angle looks like. Any questions on curved surface so far, or really any of the orientation of codes? All right, so now that we've got over the piece there, lighting, we look at this, lighting. Top, 4 most important things when we're looking at, this kind of barcode reading, again, because it's that signal to noise. Where this then comes in, next is the sensor. Lens, sorry, first lens, then sensor. So the lens is also, in the optics, is also going to be very important. You can see the light's going to come in. Our imager is not producing any light. Everybody always talks about a camera seeing something and like trying to physically do something. It's just receiving whatever it gets. The lens is there to make sure that light hits the imager in a proper spot. You have to size your lens in order to get all of the light to hit the sensor and not have some of the light either missing, where you're missing part of your, the image that you're trying to see, which is fine. But if you ever have it too small of a lens where we're not hitting the entire sensor, that's where you'll see that vignetting. If anybody's ever seen that on typically on a filter now on Instagram, but it was what usually was defined by an old-timey photo, because that light was lensed to the center of the object. And you would have the edges that didn't get any light because it wasn't lensed correctly. And all of it just trying to get that information back to the surface. So the 3 things you're going to get when trying to solve an application where we care about lensing is going to be our field of view, our focal point, and our depth of focus. So, field of view, what is it?
Like how flat it is.
How big?
Versus conic.
Yep, it's how big. We got it, yep. So how big the image is what our field of view is. So it's like it sounds, it's a pretty straightforward term. It is the field that we can view in the image. We have our focal point, which is going to be that point in space that we want to be in the best focus. That's where we're aiming to focus our image. And then we have a depth of focus. So if if I have a camera focused 5 feet in front of me, that's going to be in focus at that spot. But I'm still going to have some focus depending on what I'm trying to do before and after that case. So let's think about our eyes for a second. When we're, I think about grade school when I originally, saw this type of application, and I can only see 10 feet in front of me. That's all the focus I have. I cannot see past 10 feet. So that is my focal distance, and I have a little bit of range within there when I'm staring at an object there that I'm still going to see in focus. But it's all application specific. If I want to know if there's a tree outside, I don't need to be, my depth of focus can be very large because I only need to know that it's a tree. It doesn't have to be in perfect focus. If I'm trying to look at the leaf on the tree, now that changes. And so that same kind of thing goes with the applications we're working on here. If we have a very big code, then the things that we're trying to see and resolve, a little bit of blur isn't going to hurt us. But if we're trying to be very specific, that depth of focus is going to change. And so we look at depth of focus much more of an application basis than we do as a hard and fast fact about what our depth of focus is on an object. And you can see with this, depending on the lens that you put in there, these are our types of lenses. So we call them, SD, HD, UHD. Everyone's going to have different terms for lensing when they put into barcode readers or machine vision systems. But they're all going to relate to some kind of focal length of the lens. And again, that's a difference from focal distance versus focal length. Focal length is referring to the back of the lens, face of the lens, either way, to where it hits the sensor itself and what that length is. So that's defined for how you can actually focus that sensor, and that millimeter is going to give us a different width here. And then we're going to focus this by turning the sensor somewhere closer, further away there to get a focal distance somewhere in this range. But this is going to define our field of view based on where we are. So you could take a 16.5 millimeter lens and put the object far away, or you can take a 5.2 millimeter lens and have the same field of view at an inch away, or very close. And you can see the calculations down here with these types of lenses. So if I'm a foot away, I'll have a foot field of view. In this case, if I'm a foot away, I'll have a 1/3 or 4-inch field of view. In application, this is what that's going to look like. And it really depends on what you want. I may need a big field of view, but that means I'm not going to be able to see as much detail in the area with the same imagery. And same here, I may want a more zoomed in so I can see the details that I have in that image. So we're playing with the idea of do I get a high-end imager or do I get the correct optics? And that's just a money equation in the end when you're going with it. Then there's another thing you can do on cameras now, and this is what we're using in our cell phones, which is a liquid lens. What a liquid lens is it's two surfaces. So you have your normal lens sitting in the back. And then on top of that, you can kind of see that little ring there. There is more or less a liquid and a water that are separated. And then the light, when it passes through, and we're going to apply a voltage to those liquid and water, and they're going to shape our lens. And that's going to curve how the light comes through. And so we can do what's called autofocus with a liquid lens. So that way, without having to mechanically move a lens, in order to do that, it's just going to curve the light to get into there. And that's the same thing you're getting in cell phones. There is a speed amount to it, to try to find those focal pieces, and you are going to have a little bit of distortion, that it isn't as high quality of a representation of the image because you're going through that type of lens as you would get, looking at a standard glass or a higher quality lens. But ultimately, it's all coming back to a sensor. Every pixel on the sensor has a value, and you're trying to make sure that those values are going to give you what you need. So you can see a 0.34 megapixel camera looking at that C4 in the image, same image below. If we move that up to a 1.2 megapixel image, you can see how much clearer that C4 becomes. In this case, we haven't been talking about OCR or optical character recognition. It's fine here. You have enough pixels there. You usually need about 30 tall to see that letter C. But if you were trying to look at another image that had a smaller amount, that may not be able to be resolved. So that's where you want to look at what kind of sensor you're using and what kind of field of view you want, so you're not over-specifying on either. So then once you have those, here, let me do this slide first. I moved these two around. So you can kind of see what happens there when you're trying to resolve an image. So you have the overall image of the barcode, but ultimately every element of the barcode is going to be broken down into those pixels. And I want typically about 3 pixels is good, 5 pixels is more than enough, and then you can go down to 1 pixel per element, but you're starting to push your limits on readers at that point. Which makes sense, because if I can't see it, how am I supposed to decode it? And that's why when we look at that image, I need my image or my field of view to be big enough that I can see the whole code at once. And then I need enough resolution under there that I can decode the smallest pieces of information. So, to go back, I love this image. Where's the barcode on that image? This is why we need quiet zones.
Right third.
Is it all a barcode? Is it just that one code up in the kind of front left? I've never tried to put an actual decode on any of this. It's just a cool image that someone put together on the webs. But yeah, you can see right there that this is just codes on top of codes. And if I ever wanted to try to distinguish it, I couldn't, because there's no way to know where a code starts or where a code stops, other than maybe that one code up front that has the quiet zone. And so we think of what it takes from a processing standpoint. So everything we've done so far has been to try to make our image as good as possible, so we don't have to spend a lot of time, AI, all these other things that are out there, to try to analyze the data. But in the end, we're going to have to get to that point where we're decoding that image. So we have our image. We've done everything we can to make the best possible image. This is where we hit this. So locating first. A noisy image is going to take longer to decode. Just like a cluttered house is going to be harder to find something than a nicely organized house where you know something is. Same exact idea. And the higher resolution sensor, if we're looking at a bigger area with more pixels, is going to take more time. We use that same analogy of the house. Even if it's clean, and even if it's obviously there, if you have more spaces to look for it, that's going to be harder to look for it. And I'm going to go one past that. And this, I like to go on tangents sometimes like this. If I'm looking for a very specific item, I'm looking for my watch, my smartwatch that I want to wear out that night. If I have a big house and one watch, it's tough, but it may not be that hard to find, because it's one watch I can go through quickly. I can have multiple people go through the house and find the watch. That's fine. If I take that one step further and I have a lot of watches or a lot of things that look like watches, it's going to be a lot harder to find the watch that I want, or even the thing that is a watch. And we've done this with, the Where's Waldos of the world forever. If you have one very specific thing you're looking for and there's nothing else there, it's easy. But the more clutteredness, the more data, the more other things you put in there, the harder it's going to be to find this. And this actually comes out within our algorithms in an application that I ran into, even with knowing everything we got through here today. Normally, I think more resolution, the better. That's great. I want more resolution. Well, if we look at this this image that we looked at a second ago, and we have a nice 2 pixels there around that square. But let's say we zoomed in and we had 30 pixels, 40 pixels on each square. When I run my decode algorithm, I may actually look at that square and think it's an entire barcode itself. Because you have so much resolution on there, you're gonna have variation across the image. So you actually don't, there comes a point when too much resolution or seeing too much can be a problem, and you wanna actually back out a little bit, have a little bit less resolution, or even dumb down the image if you have a big code in order to make it so it's a little more manageable to see. And I think a good one for that is those images that are made up of like pictures that are pixels that make up an overall image. If you're very close, you'll never see that image. But the second you step back and close in on the resolution, it's almost like, you know, a perfect image and you don't see the tiny images that are hidden within there. So it's not always more is better. It just isn't. So then finally, we have all of our, you know, decoding and everything else. The other one I wanted to throw in here is understanding the differences when we're talking about decode and shutter speeds and shutter types is the difference between feeds and speeds with a barcode. So you can see at the top, one is looking at shutter speeds. So I know we don't have any photographers in here, but I'm sure people have seen the idea of like photographing a city street or a long exposure with cars driving by and you get the streaks of lights. That's what's happening when you're a slower shutter speed, is I'm going to collect that light over a longer period of time. If everything's stationary, that's great. That means I can let more light in and allow my sensor a better chance at maybe decoding. There are benefits to letting less, having a smaller aperture and doing like a pinhole lens where I only let a very specific band of lights. I have at least a couple glasses users in my class today. If anyone's ever taken their hand and like made a small hole and then looked through it, you can actually bring something into focus, even without glasses. I anecdotally learned this in like 3rd grade. Someone, I was like sitting there and noticed it. But that's the idea of the pinhole camera effect, and that's how cameras used to kind of be. They weren't lensing, because all the light's coming directly from one source. It's not coming in at angles and giving a blurring effect. So having that gives you bigger depth of field, but if I can't get enough light, I don't have enough light coming from external light, and I have to leave that shutter open and there's movement, I'm going to have an image that looks like that. And then if you look on the second one, there are something between called a global shutter and a rolling shutter. Does anybody know what those two items are?
I don't know what a global shutter.
Okay, but you've heard of a rolling shutter before?
Yeah, it's basically an open bar back in the old SLR days.
Yep.
You get an image like that if it's moving too fast.
Yep, and that's how. So when you look at the actual sensors, they're going to be one of the other two. The rolling shutter is going to be your lower cost. So if you want to have a higher resolution sensor and still be able to handle data processing, it's basically bringing those. It's analyzing each row at a time. So looking at this image, it's analyzing a row of pixels at a time on the sensor and binning those and then sending them to the camera or to the decode board. Whereas with the rolling shutter, with the global shutter, the entire pixels, the entire array is opened at once, and it brings all of that information in at one time.
But in this case, we're talking an electronic shutter.
Correct.
Not
yeah.
a mechanical.
It is not a mechanical. It's how the actual electrical signal moves across and bins on the camera.
It's how it's scanning the
Yep.
image. Okay.
It's how it's analyzed. It's how it's you physically open a shutter and close it, and you're also analyzing each row and collecting the data through a data port. And so that's how, depending on how the camera itself, the chip, the G Pixel, Sony, all the different chip manufacturers out there, they're going to have one or the other. Rolling shutter is typically cheaper and typically are released at higher resolutions earlier on. Global shutters are more common now as we're getting better with the technology, but you can see what happens if you have a moving object with a rolling or global shutter. And you can see with this image, the object is moving right to left in this case, because it first, in the same position, saw this, and then it had moved a little bit, and then it moved a little bit, and then it moved a little bit, and so you're kind of getting that blurring effect. Something that might have seen before with like progressive scan TVs when those were building up their images. It's actually how something like Duck Hunt or those games worked. Was it would leave that pixel open as white, and the camera would see the white pixel when it was scanning through there. And as you slow it down, or if it's ever not tracking on a video, you would see those lines come across. So You need to think about both of those when we're trying to do the imaging. And that comes down to the calculations of the feeds and speeds. So typically if I said how fast is your application? Let's go with a bottle moving on a bottling line, something everybody can think of. How would most people describe that? Probably in the first one, right? Typically, you're going to think about it in applications of feeds. I'm producing 2,000 parts a minute. So I'm trying to scan 2,000 parts a minute. Well, depending on what that looks like, that may not be the only piece of information I need, because that's going to tell me how much I need to decode, typically. Because that's how I have a minute, and I need to be able to read X amount of barcodes a minute. What if instead of being a bottling line with a bunch of bottles next to each other, I'm trying to track bullets coming out of a gun? Well, when it's actually moving by the camera, it's going to be moving by extremely fast. And there's going to be gaps in between taking that image. So that's where the speeds come in. So when we looked at our image before of our shutter speed and it moving, that's going to be more based on the speeds, how fast the object's actually moving in front of it, our ability to decode how fast our camera needs to take the image from the image acquisition through outputting data. That's going to be really what we're calculating on the feeds. Yes, they're related, but as far as application-wise, this can be very, very important for how we solve this. So, you may have large gaps in between timing. So I may have an object that takes a picture of 100 codes at once. If that's the case, then I'm going to be much more, caring about the feed to know how many decodes I have to do in a period of time, but the speed is almost zero. Because when I take that image, it's still, but I can still read 1,000 barcodes a minute because I'm reading a rack of barcodes and having enough time to decode each one. So, again, looking through this, that's where we get lighting source, the object, detection, and then, I know it's last, it has less words to it, but how important the decode is on how that actual decoding works on the unit. And what we're able to do from a processing standpoint on readers in order to find codes easier, quicker, and decode them faster. So, while we're still talking about the actual print quality, and then if we want to take like a, I don't know, timing here, we can finish through it, or if we want to take a couple minute break, we can, and then talk a little bit more about quality on printing and creating of codes. But now, if we look at all of them, we were narrowed down to 2 and 5. If we had to go back and pick one, what's everybody think? Not number one, but I mean a single option. Are we leaning more towards 2 or 5? And if we can see a show of hands, I'll go 2 first. And that is a fairly big room of hands, and then let's go 5 next.
Most difficult?
For easier to read, sorry. Which one's going to be easier to read for us given everything we talked about? Any 5s? Yeah. So, are they all going to be readable? Absolutely. So I don't want to get past that idea. If you take a modern barcode reader that's been, properly configured and everything else, other than 1, and maybe 3, depending on the makeup and the exact color of red and the exact, because it would have to be the exact wavelength of red that we're shining. Everything's going to be readable except for maybe 1, because physically you could screw up 1 without me being able to fix it. But everything's going to be readable. There are ways that you can do morphology with an image to fix something like this. This one, I get enough information that I assume it's good, but honestly, 5 might be the most difficult here to read in general, because you are directly getting away of the most important thing, which is finding the code. If I can't find the code, it doesn't matter how good my decodes and how many, algorithms I can throw around this. It's important to be able to find the code. I can stretch an image pretty easily. That's just as much as I can make that larger in Paint. I can have an algorithm that unmakes it larger as well. And like we said, if we just drew this code, and let's say we covered up that part with white paper, it'd still be a perfect, you would look at that code, if I just removed the top out, everything above the bottom of the 2, you would have said it's a perfect code. You wouldn't even said it's a problem at all. And that's kind of when we think of this. And I've seen too many specifications written at companies, too many quality control documents that spend all their time talking about this. Here's the problems we're seeing. We're having damage on our labels. This is what we need to focus on. But they are ignoring the fact that their real problems are coming from problems like this. But visually, we don't think to look in those directions. So that is, ultimately the easiest code up here in production to read with a imager or, a raster line scan. So well done on the getting the answer right from the beginning. So do we want to, I know Matt stepped out, but I don't know if we want to take a quick reset of a couple minutes and get water or anything, or if we've got probably 10 more minutes of going through, 15 more minutes of going through kind of quality a little bit. Does anybody need a break?
Yes.
Oh, we were talking about maybe a quick break before we dive into the code quality side of things.
Cool.
Does anybody want a break, or do we just want to?
Buy a break.
Okay, yeah, let's take a quick break on that, and we'll talk a little bit more about the barcode grading aspect of this.
Click on each one and we'll export it.
Yeah, start getting into barcodes,
I should probably do that with what's mine too.
All right, are we ready to jump into the last bit here? We'll have like 15 minutes, and I'll actually show what some of this goes into. So who has ever, everything we talked about was how can we read codes. We have no choice in everything we talked about ahead of time of how we make them better. It was all just, we're given a situation and how could we read it? And there are even many things past the basics we went over, things like, line scan cameras and the ability to rotate objects. So if you had a tube, or one common application I've seen over the years is lithium-ion batteries with a larger code that, maybe would have been difficult to read with any of the type of readers we have. You can do line scan cameras in order to build the code over an area. Or if you need more resolution, you can do that. So there's always ways that we can throw money at a problem. We know that. That's most things in life. But what happened in the world is the end customer pushed back. Because the end customer, whether that be large logistics companies, big box retailers, hospitals, consumers, got to the point where errors were not acceptable. If it did not read, it was not a product. And that is the ultimate world we live in right now. The label is as much a part of the product and is as much as important quality as anything else. And you will see it at the grocery store. They will not type in a number a lot of times anymore. They are instructed that if it is a bad label, if it does not scan, that product gets set aside. If it got damaged, then it's up to debate as to whose problem it is. If it was a bad label, then that's a fine. If it's a medical, it might be a recall. These are very, 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 very expensive things. Home Depot, Dick's Sporting Goods, Walmart, Costco, all of these are charging chargebacks to any consumer product that makes it into their facility, both for the ship back of the entire shipment with one bad label, as well as the fines that go along with that, and their revenue streams now. And so they are looking to find this. The more and more it goes on. On the medical side, we're trying to get to a point where we know what every product that makes it into a person's body that's used, and it's tracked in perpetuity. So there's the Good ID website with the tracking of the UDI data, where we need to be able to find the entire life of that product, which is all a serial number or a global trade ID number, GTIN, tracked back to a product. So in order to do this, like we said at the beginning, there will come a point when a label is created bad enough, like we saw on those screens, that we're going to need to act and try to start getting better at the beginning, and not expecting the hospital to have a $10,000 barcode reader with all the resolution in the world, or a moving object that they're going to steadily move across. It's just not going to happen. So what we then have, and we'll get into it, is something called barcode verification. So it's the line in the sand for everybody that says, here's what the standards are for marking the codes. So we need everybody to meet in the middle and be able to read those codes. So if everybody marks to there and everybody makes readers that read to there, then we know we have a usable system in the market. But even if we do everything right in the creation stage, even if we don't do the things that we saw on that first sheet where we, in all the readable codes, or sorry, in all the unreadable codes, not the readable code that was clearly damaged, but if we properly print them on the right direction on an object, you know, all of those things are set up, you're still going to have issues with the printing itself. You know, if it's a label, you know, you could have clogged, you know, ribbon wrinkle. If it's the CIJ printing, you could have clogged jets. You know, if it's a laser marker, you could be, you know, over or under heating the surface and not actually, you know, marking the product. So all of these things could be happening, and they are happening. And they're happening because typically we're going with that mentality we said at the beginning, which is, it read right now. You know, it worked in this one instance, on this one day, by this one operator with this one reader. That's not something that's going to last through the supply chain. So if we look back and understand that all of these things are going to happen, even in the best operation, we need to be able to catch those and we need to be able to fix them before they become a problem. And you can see what happens. It's the labor costs, it's the relabeling, it's product recalls, it's rejected shipments. And then down to the intangible pieces, which is customer satisfaction. If I go up to try to, you know, buy a container of milk, and I used at the beginning, and it doesn't scan, now I might think again about picking up that container of milk. On a more electronic side of things, there are security cameras, like consumer grade, you know, all around your house type cameras that typically, and these aren't just cameras, this is any kind of home automation devices that typically have a barcode attached to them. If you buy one of those and it doesn't read, it's going to be really hard to hook it up first. And then you're going to be much less likely to go buy another one if setup was difficult. And that's what it comes down to with all this. So even when you look at the actual, you know, fines and money it costs, that's one thing. But the consumer side of things and not being able to use the codes that are there for their intended purposes, you know, that's going to cost a lot more. So what was created, and this is from the earliest standards, is something called barcode verification. So you take each of the codes that you print and you give it a bunch of different categories for us to look at. These are all the same things that we talked about at the beginning in quality. But you give them grades. These grades are standard either for labels, it's a specific standard, the 15415 for data matrix and QR codes, 15416 for linear codes, and 29158 for any direct part mark codes, meaning you have a rough surface or it's a little more lenient because you know that you're probably using a direct part mark reader to read it that has some of those cool lighting options that we looked in the standard about. And then you're going to take these and it's going to be weakest link. So whatever the worst grade that you get on any individual category is going to be the overall grade of the code. And you're going to use this in order to improve process and to stop other people from saying that you weren't doing what you needed to do from the start in the plan. So it can be used both for, you know, process improvement and for regulatory purposes, depending on the industry. And you can see there, even the X or even the 0 codes, something like, you know, one of the MicroHawk readers, something nice out there that has it, that we paid attention, did all those other things to make sure we specified right, we're still going to be able to read that code. But that doesn't mean a person with a handheld reader at a hospital is going to be able to read that code. And that's why there's a big difference in looking at the quality on them. And when we start looking at this and we start talking about those barcodes, if I'm creating a new product and I put a barcode on it, you're actually going to want to look at standards. So there is you know, a way you could set these up to actually be part of the GS1 standards, because the code that I put on the outside of a pallet that's going to go through a logistics facility and read by cameras like, you know, where our projector is up there, we're going to want that to be a big code. In this case, big codes are good. And we talked about sometimes they're not, sometimes they're. In that case, the big code is good. But if I was to try to take that same code and say, well, if we go big here, we'll just go big everywhere else, and I try to take one of my handheld readers and read that code, I'm gonna have to stand across the room. Like I wouldn't be able to get the hand in hand to read it. And so if you try to do that, that same code is not applicable in the same situations. So there are standards like GS1 that have set up categories for each of these codes so that it's not it works right now for me, so everybody else should be good, but it says you need to have this size code at least, or you need to be this small for this situation. And they're all defined for the different areas of use of the codes to take it to that next level. And then we have to actually encode the data properly, as you'll see here. So imagine with barcodes that we've had over those other processes where we're looking at, kind of just the internal tracking of a part, and I was to just, let's say we look at addresses, that's the easiest way. So if I told you I live at, 135 456th Street in, city, state, I would know where to go. It's defined. They're in a specific order in order for me to find the house number, the street, city, state, zip. If we put those in any random order, you could easily end up at 456 123rd Street. Or if you look at, the fact that, Europe and the US rate dates differently, sometimes it's obvious. You can't have a 13th month. So I can decode it because that's different. But if it's January 2nd versus February 1st, if it's not labeled, then I don't know which one it is. And so there's something called the standard. So GS1, HIBCC, and there's a couple different ones. These are the same people that define UPC codes, that define the products, and they give very specific orientation to codes. They have function characters at the beginning that tell you what you're about to read, whether it's a product date, or if it's I think these are actual numbers for it, but date code, lot code, expiration date, we need to know what those are. Because again, maybe if I encoded incorrectly, my manufacture date may be on there, but I don't need an expiration date. But I look at it and I assume that's the expiration date. And now all your product goes unsold because it expired the second it was made based on improper encoding. So all of this can be done within a system. It's all encoded a specific way that you can look at with barcode verification. And you can see the kind of value it comes back with. It's, it enables the full line traceability. It allows real-time symbol assessment. It's not looking at those codes that we saw at the beginning and saying, well, that looks pretty good to me. And then you end up with one that has very bad quiet zone. And then it allows to make sure that it will be scannable, throughout the different processes. And ultimately, if you're only looking to see if something's good, then you are going to fail. It's inevitable. Because we already know there's issues. We already know that problems are going to happen. What verification and what, quality checking in this case, and really looking at it more as a product quality as opposed to a label quality, is we're not going to go all the way down to that damage at the bottom. We'll catch it when it gets to a C. Well, it's still perfectly readable. We can, replace that clogged jet, fix our speeds, fix our feeds so the printing is a little bit better, reevaluate the material we're printing on so that, the phone camera can read a little bit easier in that case, and you'll catch it before you ever have a problem. And so this is what barcode verification can do for you. And so if we look at a code that I have here, we created a card that has a bunch of different codes on it. Now, right now I'm using the label quality one, so it's the stringent one, it's not the direct part mark. But if we want to, we can go back here and look at that. But you can see, good code. A little bit low on contrast. Oh, sorry, no. You guys can't see anything. There we go. So you can see that it's a little light here, but there's a blue box around that code. So you can see that the contrast is a little low. This is expected. I'm printing laser etched on a black material, and that gray is just a little gray. It's not very bright. But overall, very readable and a 3.0 grade. If you ever see these standards, we're always going to have this up here. You have 3.0, that's our grade. That'd be a B in standard, grading. like high school grade levels. 10 is our mill size, sorry, that's the aperture used, so that's the laser dot or analytic view that's being used to analyze the barcode. This could be changed. Right now it's set at half, because that's typically what the standard has. If you had very specific applications, you could change that to be a different size, so it matches whatever my barcode readers in the field are going to be. You have the wavelength of light. This is our red. So now this would actually analyze if we had a red barcode, and you would know that the standard 660 nanometer wavelength of red laser that people use. And then D is our dome light. So it tells you what we're using. So this is being scanned with a dome light, and you can see that right here when I pull the trigger. The lights around the edges are aiming up, and we're getting a nice, even red light on this verifier. Now, let's go to the axial non-uniformity code. And you can see there, looks like one of the codes we saw before, right? The one that was stretched. And that one comes up as decent and everything else. 3.0, 3.2. But axial non-uniformity is off the charts bad. Then we can go to one of the other codes. I don't know what's, I assume modulation. I know this one says modulation, but I don't know how he marked that as bad modulation. It looks like good modulation to me. Modulation is the differences, so we'll go back to the waveform and thinking about data. Contrast, as you can assume, is our amplitude. It's what is the difference between our light and our dark. Make sense? Head nods? Modulation is going to be the difference in our peaks versus other peaks, or our valleys versus other valleys. So if we look at, as a waveform, what we're trying to do is have all of our elements the same black or the same white. That's not always going to be easy to do, both from the marking technology or our background. We saw those metals where we had bright edges. That's where modulation is just going to kill us in lighting. And so we want to do our best when we're creating the barcodes to have good modulation, have even backgrounds, have even marking, so that we don't have that problem. Then we can go to something like print growth, which we saw on the bottom left. What do you think this is going to be affected here? Which category? Let's hear a couple guesses. Throw them out. You won't be wrong. It's going to be a couple of them.
Non-uniformity too.
Grid? I'm hearing a couple. Anybody think anything else? We'll go with grid. So grid non-uniformity is, will the overall thing line up? Oh, and we're not even, it's not very over printed. So it's still actually pretty decent there. Our laser marker was too good on making bad codes. If you do have significant overprinting here where our cells are smaller, modulation is where it's going to affect, typically. Because what happens is if I overlay my grid and it still fits in a square, my grid's good. Now, if you have something like...
Can you bring up the 2D analysis?
Yeah, absolutely. I'll go that on this one. This is a perfect one to show it. I'll show that on this one. So, grid non-uniformity is going to be heavily like this, where it's no longer a grid. Part of it's been stretched out. Maybe the metal is deformed when you tried to mark it, and so it was at a curve, and then you flatten it back out, and now that has a different shape to it. But maybe we want to look a little deeper into this. So we can go to our 2D analysis. I have a feeling this is going to pop up on my screen. So let me find my cursor. So, you can see we do have these spaces are smaller than our marks. And it's very noticeable in our clock pattern. What that affects, and in this case, it's our darks are so dark that it's helping us. If this background wasn't such high contrast, we would probably be having more issues than we're actually having. But if we look on here, we have some numbers down here at the bottom. So we have our lowest reflectance module, and we have our highest. So that tells you our contrast. Again, that's our differences in, our highest and lowest. And then we have our lowest modulation module, which is actually not too bad. But what it's measuring, if we look, is it's overlaid our grid of data, right? All of our information. These are the modules. Each of these are going to encode a specific piece of data, like a letter or number. And that's why you have redundant data, because there are more up here than there are bits. So you'll look at this, and once we know our clock pulse, and we have our locate pattern, we can lay this grid over. And then we're just analyzing. We say, is this dark or light? Well, it's at a 5 contrast total, so that's light. We're going to go to here. Is that light or dark in that, space? Well, it's 62. That's light. So our significantly darker background here is giving us the edge on having a difficult modulation. If our background was less consistent, our modulation would go up a lot, because what happens is somewhere like here, we're overprinting on the top, on the left, on the bottom, and not on the right. So because of the overprinting coming in at different amounts from each side, you're going to have a lot of variation in how dark your dark spaces and how light your light spaces are. Right now, this material is so very dark that it is absorbing a lot of light and helping us on the overall grade quality, but you can see how that would affect your modulation scores on here.
How are scores usually requested in industry? Would they say like it's got to be on the grade scale, it has to be above a certain grade? Or
Yeah.
just
So typically, the way, and great question. So typically with different industries, it's going to be considered by a letter. The actual organization, ISO, has gone away from letter grades because they're too, there's not enough detail. We need one more decimal point past that. But that is referring to a 1.5 being a C, rounding up to a 2.0 or better, is what typically is required by most industries. Internally, a lot of people will strive to do B or better, meaning 2.5 or better. But industry-wise, when you look at what's required by most consumer big box stores, what's required by UDI for medical, what's required by the military for UID, what's required by the Pharma Serialization Act, that's all going to be C or better, because when they were written it was a letter-based scale, but that means 1.5 or better. Both of them are synonymous when you look at the grading. But typically, if someone asks us to tell you that it's a C or better, we'll say a C is 1.5 or better. We are going to hold to 1.5 or better because the standards say the otherwise. Otherwise, people will say we want to be ISO compliant or GS1 compliant. If you say either of those, or UDI compliant, or whatever level, UID compliant, those are documents referencing other documents referencing other documents. So if you are referencing any of the specific standards, typically you are going to go back to, UDI is going to go back to GS1. GS1 is going to go back to ISO. And ultimately ISO says a code is good if it's at 1.5 or better. So they may refer to it many different ways, but typically it will go back to that number itself.
Got it.
I have not heard of anyone externally allowing for lower than that codes. No one's ever allowed for Ds. I have had some people ask for more. And where it becomes more important to me is that example of consumer good. Like, it's less about the standards in my mind out there, and it's more about if you have contract manufacturer, you are doing work for someone else or they're doing work for you, making sure it's laid out and it's clear. Because, if you tell me to have readable codes, then it's a very arbitrary, unenforceable thing. So this just, again, makes that line in the sand that allows everybody to meet in the middle. And then you can see the opposite over on the other code here with underprint. So contrast is a little low. Typically, what do you think is better? Would you rather be underprinted or overprinted? and maybe a quick why.
Underprinted, because I think if you overprint, you risk bleeding into each other, and thus you can cause like broad metrics. But underprinting, the primary characteristics are still going to be hit.
Yep. Very astute and absolutely correct. Where the underprinting hurts you is contrast, because there's less marking on that surface. And again, if we go back to our 2D analysis of this code, but what you're gaining is the markings are not interfering with each other. The spaces that have no marking are all the same, and the spaces that have marking are all the same. You will have a lower amplitude total on our, look at our total waveform of what this looks like, but they are not encroaching on each other's information. So contrast goes down a little bit, but the data is not, and you can see that when we look at the squares. So we can see that our contrast, we were in the 60s typically everywhere else, now we're in the 50s, so it's a lower contrast, but you can see that nowhere are we having any problems with 4s having any white in their elements. And that would be so counterintuitive if I was printing, if I didn't know what I was looking at. If you look at those two codes, and knew nothing about it being machine readable, I bet you it's 9 out of 10, maybe 10 out of 10 operators would try to make this code before they try to make this code. Because as humans, we're contrast oriented. That's all we think. That's when we look at an object, we think, like, I want to see edges, I want to see this nice visible object and then this not very visible object. You see that and you immediately, you want to do the one that has a lot of print growth. And I saw this with a respected engineer at the largest printing company for labels. We do a lot of work with verification with Zebra printers. They're, the standard out there in the world, and or at least, one of the most used. And I asked one of their engineers that it showed to print me a couple labels that I could put under the verifier just as a demo, assuming that it would print a perfect label. When he printed it, he knows how to adjust the settings well. Their logo looked beautiful. But in order to make that logo look pretty, that was really going for contrast. It wasn't going for data. And the code created a V by one of the engineers that had all the access to do all the printing there to show. And it was just his human nature as someone printing out labels to make the logo look good, which meant high contrast, meaning it popped off the page. But when it came to the thing that everybody really cares about with the barcode, because one's consumer facing, one's the actual usage of the code, which that's what barcodes are there for, it was failing. It would have cost him money if that made it on a package. So that's the basics there, and then you can see if I was to go here into setup and go to the direct part mark algorithm. So these are all the different standards that exist out there. But I can go up here to the ISO standard for DPM. We can go back to our grading tab. And then, if I have a tougher to recode, like these, I can set this on here. I can hold down my reader, and it's going to change settings, use different lighting, like the dome light, in order to get us a grade on that code. And look at what that light looks like. Just like we talked about, dome light, all edges. Read that code all day long, no issues. 4.0 passing. I can go into my lighting here. And it's coming up on my other screen. And I'm going to turn off our red dome. And I'm just going to look at the low angle lights. So let's see, I'll just turn on north-south and then we can
Can I interject with a question?
Yeah, go ahead.
A member in the chat asks, is there a minimum cell size for 2D barcodes, more specifically to be the most decodable across multiple varieties of scanners?
So it's going to be based, so that's the part we were talking about a little bit, that's going to be based on the application. So if you're talking about GS1, and we're talking about the tables, so GS1 has a table that says And let me go right into that here. So before we go into lighting, I can go into setup here. I can go to GS1 Gen Spec. And here's all the categories that are going to determine what the correct size, the optimal size for a product is. So, is my item being scanned in general distribution only? It's going to be a lot bigger code that we're going to want to do. If it's a small code, I'm never going to be able to read it from an overhead code. Am I going to have a code that's going to be a trade item, that's a packaging container, not scanned at POS or general retail? So this could be different. This could be the box that's on a pallet. Then you might have one that is, scanned at general retail, POS, and just general distribution. So this is how those optimal code sizes are done. There is a range of sizes for something like a UPC code. It should be a 10 mil code. Yeah, I think it's a 10 mil code plus or minus a percentage when they refer to it. So it can be 80% of that or 120% of that. Anything outside of that, you would not be within spec of a UPC code. But that's what, that's what application people, that's what, someone like myself or Omron or Mechatronic, like all of us are here to find that right person to help you with your standard. Because you don't want everyone in the world to be an expert on barcodes. That's never what this training or what we're trying to do, but it absolutely depends on the application of what the code's being used for. Because in some applications, you want that thing as big as the side of a building. I mean, that it really is, there's codes that need to be that big, and that's the only way they work. And other times you want it to be, on the head of a pin. The keys, though, on size, if you have your own choice, is making it fit within the surface. So you don't want to oversize the code for the printable area. That is a lot like what we were looking at with this code here, or some of those pictures I showed before. So let's go back, now that we talked about GS1, let's go back here, go back to DPM, go back to our grading. And we're not going to see this here. So there's our image. It was still up there from before. I'm going to take a bad image here, and it's not going to work well. It's not going to work great. Oh, there we go. We actually got a decent image out of this. Let's turn this so I'm actually looking at it correctly. Oh, there. We found the code there. So in that, pull the trigger again. In that case, that code itself, let's not worry about the actual grading piece, but you can see this code is sized for this part properly. If it was not sized for the part properly, this would start bleeding over the edges. This, if it got too long and it started getting towards the ends of it, then that would not be sized properly for the part. And this could be everything from, when you put a printing pad on a product and leave an amount of space and you don't give enough quiet zone for that product. Or I've seen, people put other things on labels, like to distinguish that this product is, and I see it more for medical, but like this is meant for a certain purpose. So you put like purple on the sides of the label. And this is another label I'm putting in something like a sticky note where I put red on the sides of the label. Well, if you put your code on and put those things on, those are going to start encroaching on a quiet zone. So I would much rather have a smaller code than a bigger code, even if the resolution starts to fall off. So it really comes down to really fitting your code for what you're trying to mark it on. And then picking a reader that will work. But yeah, in common, if you can print codes that are around that 10 mil, meaning 10 thousandths of an inch, element size, those are a pretty optimal spot. And the other thing you have to think about is what's marking. So you can do anything to try to fit a code perfectly at a spot, but all marking systems have a resolution as well. Whether we're talking about CIJ before, it's shooting a dot of ink out. That dot of ink has a size. I can't shoot half a dot. I can shoot 2 dots. So then I have to start doing percentages of whatever my marking is. So same thing with the thermal transfer printer. Those elements have sizes. You'll buy a printer that is 200 dpi, 300 dpi, 600 dpi. Those are dots per inch. So if I'm trying to size my barcode for a label, and you have proper software, it'll do it for you. But if you don't, and you're trying to stretch an image in Word or trying to fit it to some other kind of, design file, then the size is going to have to be a multiple of whatever that dot is. If it's a 300 dpi printer, that means your dots are 3.3 thousandths of an inch. So if you want to make a nice image, just what we saw from reading the pixels, I'm going to want to print good pixels. So I'm going to probably want 3 to 5 dots per element that I'm printing. And that way I have a nice, encoded data. So that's probably the best answer I can give for how do you size it accordingly. And then looking at this, I was just showing what happens, this is north and south lighting. So you can see it actually is wide enough on our parts. And we have enough contrast here on the part that there is a little bit of a dark line down the middle, but we are getting decent lighting back on this object. And if I turn it, you can see how those striations and the rest of the part looks if the light's going in the other direction. So you can see the modulation and the issues came up a little bit more. Now, is it fine with a DPM code? Yeah, these were very nicely marked codes. These are, well thought out, very nicely printed codes. But from a reading standpoint, that's clearly harder to read than that first one you saw when I had on the dome lighting. And if you look at 2D analysis on parts like this, you can see what the differences are in quality. Cursor. You can see how there's damage in the code. Some of them are great, even with low contrast, because contrast isn't as much part of the DPM algorithms as it is in the label algorithms because it's being marked on a surface. But you can see how some of these things cause issues with the white. These falling off and being at 70%, 54% modulation. Yeah. And then with these kind of things, it is important that you go back in and either look at structure. In this case, it's just data. If it was a GS1 code, it would actually break out what each of the structures mean. So you see what's actually in the non-encoded data. Something important if you're trying to create codes that are being used for certain industries, because there is data that's not encoded that you see. If you were to type in, and I don't have any GS1 codes around me that I know of. If you were to type in the data the way it looks, it would not be the same as what you need to encode. So that's where you want to look at actual structure. And then with any of these kind of verifying reports, you're going to have reports that you can send out or receive from people to compare to each other. In our case, we save them off in perpetuity with any of our offline verifiers, but that's the other important piece, is that tracking part of this. If you're going to do all this work to create the codes and make nice codes, you want to record that you made nice codes as well, so if anyone comes back. But I think that's all the stuff I had to go through. Any questions? Any other, barcode or vision related? I mean, honestly, everything we talked about, we're talking about a very specific data piece of machine vision, but at this point when we're taking images, it's no different. It's contrast, it's, location, detection, blob analysis. It's all the same stuff you do with machine vision. So happy to answer anything else. Otherwise, we can come over here and take a look at some of the codes with the lighting and see what it does. Good. All right. Awesome. Well, thank you for everyone taking the time to kind of get back to basics with the barcoding. And hopefully, when you get back to seeing codes and working on them, or, analyzing and wanting to get more data, that you start with a good code to make it work better along the process.
Thanks.
Okay. Thank you.
Let's play with toys.
Yeah. So I got a couple different things set up here. I have the verifier. I can plug in the handheld if you want to see.